So we're going to talk about what happens to the energy levels when you place a hydrogen atom in them. Let's just quickly recap what we did last time. So for hydrogen, we had the energy levels were En equal to minus 13.6 EVs over N squared, where N is equal to 1, 2, and so on. It's the principal quantum number. Quantum number. This is N. And then we had L, it was called the orbital quantum number. And the values that L takes depend on N. There's just 0, 1, all the way to N minus 1. And then we had an L, which was the magnetic quantum number. And these NLs, they take range between 0, plus or minus 1, all the way to plus or minus L. Okay. Now, if you have a hydrogen atom in quantum state N, it will have the energy level given by, let's say if it's state equal to 2, you will have minus 13.6 EVs divided by 2 squared, which is 4. When you divide, I forget what the number is, but you get one specific number, okay? Regardless whether if L is 0 or 1, right? If N is equal to 2, L could be 0 or 1. And also regardless of ML, whether it's 0 or plus or minus 1. However, when you apply a magnetic field, what happens, the energy levels split. So for example, for N equal to 2, here's the energy level. If you apply a magnetic field, what happens, you will get an energy level here, just like it. But then you get another energy level that's slightly higher and another energy level that is slightly lower. It will split into 3 separate energy levels. If you like, it will split like this. And the question is, why does it split? And how does it, and then what is the spacing between 2 energy levels? We can understand this by thinking of the electron going around the atom in some sort of a circle, and the circle will have a radius r. We can think of the electron as it goes around. When it orbits, it constitutes a current on an area, around an area, which is a magnetic moment, magnetic dipole moment. And if you put a magnetic dipole moment in a magnetic field, it will have a potential energy. And that potential energy is equal to negative the magnetic moment dotted with the magnetic field, magnetic dipole moment. Remember for example, the electric dipole, this is magnetic. For electric, the potential energy for an electric dipole in an electric field was minus P, which is the electric dipole dotted with the electric field. Do you remember this? From last semester, probably, right? You had EM. If you don't, that's fine. We'll just review that. Okay. Now the magnetic moment is here, or mu, is the current times the area. And we're thinking of the electron as it goes around the nucleus of radius r, so the area would be pi times r squared. The current itself is going to be the charge divided by time. So the charge is minus E, divided by the time. We'll substitute, we'll see what the time is. Now, yeah, it's time to talk about the time. So E over, the time is distance over speed. The distance around the nucleus is 2 pi r, and then the speed is v, so 2 pi r v. And you get pi r squared. Cancel the pi's and the r, and you get minus E over 2 times v times r. Now this kind of vaguely looks like the angular momentum, but angular momentum is mv times r, okay? Because here's the electron going around the circle. Let's say the electron at some moment is here. It will have a momentum in this direction, and the momentum is mv, and the position is r. So their cross product will be the angular momentum. And since they are perpendicular to each other, the magnitude of the cross product is just the product of the magnitudes. So it will be mv, but we have to divide by m in order not to change this. Now, mvr is the angular momentum, so we get E over 2m times L. This E over 2m is called the gyromagnetic ratio. It just has a name. But let's now write the magnetic moment as a vector. So mu would be minus E over 2m times the angular momentum. Okay. Let's maybe put a box around this one. Now, let's see what happens when we apply a magnetic field. Suppose we apply a magnetic field. Suppose the magnetic field is applied in the z direction. Okay, magnetic field is in the z direction. Then the potential energy would be minus mu dot b, and that is minus E over 2m, and then L dot product with B K hat. Minus minus is plus, and you get E over 2m, and then B. Now, the dot product of the vector L with K hat will pick up just the Z component of L, right? Because L is Lx I hat plus Ly J hat plus Lz K hat. When you take the dot product, all the other ones vanish except the dot product for K hat with K hat. So this is just Lz. Okay, Lz. Now, oh, I forgot to write here. Now the total momentum is L times L plus 1 h bar, and then Lz is equal to ml times h bar. We did this last time, I forget to write it. So now Lz is ml times h bar. For Lz we're going to write ml times h bar, so E times h bar divided by 2m times b. This has the symbol mu b, and it is called the Bohr magneton. Okay. I'll tell you how much it is. In fact, I'll tell you now. Mu b is equal to, I don't remember the constant, but it has a value. You can plug in the numbers to figure it out. Approximately it is 5.788 times 10 to the minus 5 EVs per Tesla, or in joules per Tesla, it's going to be 9.274 times 10 to the minus 24 joules per Tesla, or ampere square meters. So we can write this shorthand then. The potential energy is equal to ml times mu b times the magnetic field. So let's see why this affects the energy levels. Before you apply the magnetic field, here is the energy. You apply the magnetic field, the energy will change by this much. If ml is 0, this is ml equal to 0. That one is level with this. If ml is 1, then you will have here. This is the energy level, ml. If ml is minus 1, then this is ml minus 1. And so on, for 2 and minus 2, and 3 and minus 3, if they are there. Okay. What's the spacing between these energy splittings, between two energy levels here? The spacing is just mu b times capital B. That's the spacing. Okay. We'll do examples as we go over the homework, but for now this is all I wanted to speak about as far as this topic. Does anyone have any questions on this? In fact, I was going to give you a handout here. It's from the homework. Somehow the staples did not come out to be right. Again, it's the canvas, you should have it also. Yeah. So I plan to go over the homework in a little bit, but let's go to, just to show you, demonstrate how this can be done. Let's go to problem 5. We'll do problems 5 and 6. So it says, I will just state it. A hydrogen atom in a 3p state is placed in a uniform magnetic field. So here's the example. So we have a hydrogen atom in the state 3p. 3 means N is 3, and then P means L is SP, so L is 1, right? And it's placed in a uniform magnetic field. It says here, the first one, how many energy levels will there be? How many energy levels will we have? If L is 1, how many different lines will we have if L is 1?
It's just 3.
3, yeah, because L1 means M could be minus 1, it could be 0, and it could be 1. So all these, yeah. So that's correct. And and then they say, okay, great, so 3. What if, now they say, let's say the spacing between two energy levels, let's call it delta E. Let's say the spacing between two energy levels, or delta U, yeah, I use the letter U, so let me put here, delta U. If the spacing, let's say, is 2.71 times 10 to the minus 5 EVs, is 2.71 times 10 to the minus 5 EVs, what is the magnetic field? what is the applied magnetic field? How would we figure that out? This is the spacing between
Use
the two.
Use that formula.
Yeah, right here. It's, so it is equal, the spacing is just mu b, so it is equal to mu b. So the magnetic field, B, would just be 2.71 times 10 to the minus 5 EVs divided by the Bohr magnet of mu b. Since I have EVs on top, I will use the one that contains EVs, right? So that's 5.788 times 10 to the minus 5. EVs per Tesla. So the answer would just be Tesla. And if you do that, you get 0.468 Tesla. Okay. Any questions on this one? Next problem is fairly similar. And I'm going to read the next problem. A hydrogen atom in the 5G state. So it's in the 5G state. So state is 5G. 5G. So 5 would represent what? N, right? And G, so N is 5. So how about G would represent L to be what? S is 0, P, D, F, G, right? So 4, right? L is 4. Okay. So how many energy levels do you expect to have? If L is 4? 9, yeah, because the minus 4 for the amps are ML minus 4, minus 3, and so on, all the way to 4. So 2L plus 1, always 2L plus 1. So yeah, you will have 9 different energy levels. And the first question, or how many energy levels, there was one question, so there are 9. If the magnetic field is 0, if we apply a magnetic field along the z direction, and that magnetic field is 0.6 Tesla, so if the magnetic field is equal to 0.6 Tesla, so what is delta U then? So the energies would be, here is 0, 1, 2, 3, 4, minus 1, minus 2, minus 3, and minus 4, right? Minus 1, minus 2, minus 3, and minus 4. What's the spacing between two energy levels? The first one?
UB times 0.6.
Exactly. So it's going to be, so the spacing between two adjacent levels is going to be mu b times 0 times capital B. So feel free to plug it in. And then let's find it. 3.47?
Yeah.
Times 10 to the minus 5. Okay. Now, the next one says, what is the energy separation between the level of the lowest energy and the level of the highest energy, meaning
It's just not times 9.
almost.
Times.
How many spaces are there?
Oh, 8.
8 spaces, yeah. So technically here's, if you want to be more, yeah, it would just be this times 8, but here is how you, if you want to be more rigorous, if you like. So u of the upper minus u of the lower or lowest, you will have, at the top one it's 4 mu b times capital B, and in the lowest state you have minus 4 mu b times capital B, and that is just 8 mu b times capital B. And we already determined that, so it's just this number times 8, and that comes out to 2.78 times 10 to the minus